So we are done with, actually, before we start with this part, let's have a motivation for this. So till now,
Sir,
yeah,
sir, what was the total marks?
forget, stop talking about the quiz.
Okay, sir.
Yeah. So till now, we have discussed AM and angle modulation. Both of these use the message signal waveform directly to modulate carrier. Have seen the circuits that are used to generate these signals. Generate and demodulate. Seen the wear of these systems under simple sinusoids. Fine. So all of this we have covered, but uh, we have time and again argued, yeah, but have time and again argued that signals that we are actually interested in are non-deterministic. Actually, we call the proper word for these signals is random. So we are interested in random signals. That is one thing. And two, the signal or the modulated signal the has noise. So uh, that is also random. So we want to, in order to understand the behavior of these systems for random signals and under noise. First have to understand randomness. Fine. So we what is random and and how do we deal with randomness? So what is randomness and how do we deal with this? So you told me that your probability and random processes course was truncated due to a random event. So this pandemic is a random event actually. Anyway, so let's first have some, before we start, let's first clarify a common misconception that we have, or a confusion that people generally create. So let's clarify the English first. There are two words that we use interchangeably: random and arbitrary. So I've written both of these, but arbitrary isn't showing up as of now. Maybe it will show up. Yeah, now it's showing. So there are two words, random and arbitrary. So can anyone tell me? So when colloquially we use these two words interchangeably, but technically random and arbitrary are not interchangeable. Random is something that we define, or randomness is something that we'll deal with in quite a lot of detail, whereas arbitrary or arbitrariness, if there is a word like that, is something based on our hunch. Yeah, arbitrary is for no reason. Randomness still has some reason. Good. So anyway, but we tend to use colloquially, we tend to use these two words interchangeably. So for the rest of this course, we'll avoid this kind of a misconception. So now a random experiment simply. So let's start randomness. So let's start by defining
So
random.
what did you tell the difference as? Like I didn't get difference between these two.
Yeah. So actually, I haven't clearly defined the difference between these two. What we'll do is arbitrary, or these are used as synonyms colloquially, but randomness or random we'll define. Random has what is technically what is random has a has well-defined rules governing it, has a set of well-defined rules governing it, whereas arbitrary is totally arbitrary. So
Okay.
we'll as we cover this the rest of this course, this difference will become clearer.
Okay.
Sir,
Yeah, Shubhashish.
so we call a variable random when we can somehow define it in some terms, right?
So the word random variable is a misnomer. We'll touch upon that today.
So the randomness, so actually the randomness, if it can be defined in certain terms, we call it randomness, right?
Yes,
And if we cannot
in a way you are right.
okay.
Okay, so as I've said multiple times, uh, don't jump. Curiosity is a good thing, but it also killed some cat somewhere, as far as I know. I don't know which cat and where, but curiosity did kill a cat. But still, it's a good thing. Yeah. So let's first define a. No, I've thought about that, but I don't know whether Schrodinger's cat is dead. But the cat that curiosity killed is definitely dead. Yeah. So let's first define random. Yes. So you have to be curious to open the box. And when you open the box, the cat can still be alive. So curiosity doesn't necessarily kill that one. Yeah. So coming back. So that Schrodinger's cat, the outcome of an experiment whose outcome is not known so an experiment whose outcome is not known previously, or something that you cannot predict when you perform that experiment, or something experiment that is non-deterministic. For example, the tossing a coin, rolling die, the winner of a Ludo game. Yeah, so the online Ludo game, you can cheat in the other one. So anyway, so the experiment, so experiments whose outcome is non-deterministic, and so such experiments can have multiple outcomes with having different likelihood of occurring. So if there is as if there is just a single outcome, then the experiment is deterministic. So if you say that you conduct a random experiment, if you conduct an experiment and there is only one possible outcome, then obviously that experiment is deterministic. I hope that this explains it. So I'll just write it down.
So then having more sample space is the problematic.
Yeah. Can you say that again?
Because like for example, if we take multiple, if we do the experiment multiple times, we will be getting multiple outcomes. So our sample space is also means the number of possible
Have I
options are also
have I
increasing.
used the word sample space?
No, I am
Have
possible.
I used the word sample space?
No.
Yeah. How many times do I have to tell you to not jump?
Okay.
Yeah, actually, yes, have multiple outcomes. So, Aditya, I'll correct myself. So, such experiments have multiple outcomes. Now, is it okay? Yeah. So, such experiments have multiple outcomes. They don't have a single outcome. Yeah. So, now, uh, coming to what so this is a random call. Shubhashish just did some tried to make it deterministic. Anyway, so with such experiments, the set of all the possible outcomes. So whatever is possible in the experiment is called the sample space. The set of all possible outcomes is called the sample space. So now shoot your question about the sample space.
Sir, I was actually asking that if we do the experiment multiple times, aren't
Yeah.
we increasing the chances of like having chances? Aren't we reducing the chances of getting a definite outcome?
If you repeat the experiment multiple times, what you are doing is you are increasing the sample space.
Yes. So
Yeah.
if
So what's the problem?
so like just like Adit asked that question, so if we do the experiment only once,
Yeah.
so we are basically pushing the number of outcomes to lesser extent, right?
Yeah. So you if you so that is something that we call that comes under independent repeated experiments. So if you say that you uh, toss a coin 5 times, you're basically conducting one experiment where you're tossing the coin five times. So
Yeah.
the sample space with the length 2 to the power 5, if I may jump, consists of one experiment where which involves the tossing of a coin 5 times. There are not those are not 5 experiments. That's just one experiment. So you increase the sample space.
So when you said that if we increase the number of experiments, so we get multiple outcomes.
We
The
I never
experiments,
said that we increase the number of experiments.
but with one experiment we get only one outcome.
Yeah, so one experiment you will get just one outcome. You have to repeat the experiment multiple times. You will get
Okay.
different outcomes.
Yeah. So
So
doesn't
if
that
you
reduce?
say that the experiment is the tossing of a coin, you
Yeah.
clearly state that the experiment is the tossing of a coin, then you toss a coin. If you say that the experiment is the tossing of a coin 5 times, then you toss the coin 5 times, and that counts as one experiment. If you say
Okay.
that the
Okay.
experiment is tossing of a coin once, then your sample space is just 2 events, a head and a tail.
Yeah.
You can do it any number of times, your sample space will remain a head or a tail. You won't be increasing the sample space. You you say
Yes, sir.
that your experiment involves repeating the same task multiple times, then the sample space will increase.
So actually, Adit has actually posted the question that I wanted to
Okay,
ask.
is the sample space so the sample space of a random experiment is Actually, when you perform the experiment multiple times, then the sample space of the experiment will be decided. So, for example, let's take the vaccine trials. We know the vaccine trials, right? So the vaccine trial is a random experiment. You are injecting that thing into people and you are expecting some sort of things. So last month there were reports that some guy has developed spinal cord infections because of that. So that was a new event and that was added to the random experiment. So that constituted the sample space of the random experiment. So theoretical random experiments thankfully have well-defined, well-structured spaces. We are thankfully dealing with the theory. So all the theoretical thought random experiments that we'll do will have well-defined sample spaces. But yes, if you are venturing into something totally new, the sample space will have to be constructed on the fly. Yeah. So I have multiple outcomes with each outcome having a different likelihood of occurring. And the set of all the possible outcomes in these experiments is called the sample space. So, and for the purpose of this course, we will denote space using the set omega. And the outcomes small omega are elements of omega. So for
So what is that symbol?
this, so okay, for okay, just a second. For any experiment, the outcome, this is small omega, is an element of, this is capital omega, which is also the symbol for ohms. So is an element, small omega is an element of capital omega. So the sample space omega called discrete if it contains a countable number of outcomes. It is called non-discrete if the outcomes are, note that countably infinite outcomes are still countable and Just a second. Anindra. Note that countably infinite still countable and constitute a discrete sample space. Yeah, now let's read your question. Can small omega contain more? No. Small omega is an outcome, and so this omega can be only single outcome. So for multiple, for cases with multiple possible outcomes, like an even number in a die. So an even number in number on a roll of die actually contains three outcomes. Or rather, I would put it this way first. So an outcome is the most elementary result of random yeah. So an outcome is the most elementary result of a random experiment. And like I was saying that what we may want to define is a case where our desired result consists of multiple outcomes. For example, case even number consists of the outcomes 2, 4, 6 of the rule of non-discrete means uncountably infinite, yes, or uncountable. Or non-discrete means that it will have an uncountable number of events. Uh, so the sample space will be non-discrete. The number of events within that sample space will be uncountable. So the case an even number consists of the outcomes 2, 4, 6 of the roll of a die, and therefore, so full stop. Fine. So these are called events. So an event is a subset of the sample space. So an event is a subset of the sample space, and an event is what we observe. So for the role of actually this is too complicated. Coin. There are two out. A head and a tail, there are two outcomes, but you don't toss a coin, you get a head, you get a tail, you get an outcome. So the toss of a coin has two outcomes and four events. Is that okay?
So what do you mean by the last one?
So you say that you toss the coin. Any outcome is an outcome. It's either a head of a tail, a head or a tail. It contains absolutely no information, that sentence, but that is still an outcome.
Okay, sir.
Okay. So actually a proper definition of an event is an event is a subset of the sample space for which probability can be defined. So we'll not do the measure theoretic definition of. So I mean that is we are talking about an unbiased coin. So an event is so an outcome is an outcome can be an event, but an event is not necessarily a single outcome. An event can contain more than one outcomes. So
Sir, could you give an
yeah.
example for event having like only edge but tossing of a coin, like an unbiased
So
coin event?
no. So event is one tossing of event is what you observe after one tossing, or the event would be, say, how do I? So till now I've only dealt with the mathematical definition of an event. So this question is slightly hard for me. So moreover, so an event is something that you can, some outcome of the experiment that you can describe in words, or it can contain more than one outcomes. Yeah, an event can be getting heads in a toss of a coin. So the difference between event and outcome becomes clearer when we talk about a die. So, but that is slightly complicated to make. So sample space is 6. This is the sample space. So now the possible events are, I get an outcome. That is one event. Another event can be not get one specific outcome. No, event. The experiment has two outcomes, yes, but there are four possible events. So
Sir, it's confusing right now.
okay, so where should I, what point should I go back?
Sir, the thing is that when uh, Bhavnik was asking about, or Adit was asking about that event, how come it has four events now?
So it has
That,
two outcomes.
yeah,
It has two outcomes and four events.
this sample space or the sample
The
space
sample
Adit
space has
was
two events. The sample space has two outcomes.
okay.
So let's say, and for that sample space, okay, so let me define another term. So define, maybe this will make things clearer. Mathematical construct called a sigma field. You know what a sigma field is? Okay, so basically for any set, say for any set omega, sigma field is the collection of all the subsets of omega. So for any set omega, a sigma field, so or so for the sample space omega, the sigma field B is the set of all.
Sir,
Just a second, let me complete. Yes. Now,
sir, are you speaking about power set?
so yes, a power set is so a sigma field is a power set. Yes, but for probability theory we call it sigma field.
Okay.
Okay. Or and all the elements of so the all the elements of the power set, because the power set, one thing is that we use a different notation, because as of now, or till what we have done till now, power sets only defined for discrete sets. Power sets are only defined for discrete sets from what I know till now. Right? Sigma fields, on the other hand, are defined for both discrete as well as non-discrete sets. That's why we
So
use.
just
Yeah,
one
yeah.
thing, like last semester course, like sigma field, like I had read about it and I remember a little bit. I'm not that sure, but as far as I remember, if there is an element A in sigma field, then there must be a complement in it. So it can't be set of all subsets, right?
It is.
Like if the
It
sigma field,
contains the null set as well.
yeah, for the whole set, yeah, that is true. But if our set is 1 to heads, tails, null,
Yeah.
and phi, if that is the case,
Yeah.
then and if the experiment is like two coin
No,
tosses.
no, just one coin toss, because in that case, the if we're talking about two coin tosses, then the sample space changes.
Okay,
The
okay.
sigma field also changes.
Just stick with one coin tosses. If I
Yes.
just say that one of my subset is phi and h,
So your subset cannot be phi and h.
that can be. I mean,
Phi is the
what?
empty set. It can either be so each event is a sub is an element of your. So these are elements of the sigma field B. So this, if I call this a sigma field, all of these are elements of the sigma field. Their unions and intersections, yeah.
Okay.
And when you say phi and h are phi and h, then you are talking about the union of phi and h, which is h.
Okay, 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 okay. Got it, got it, got it.
This satisfies that condition of the sigma field.
Yes, yes, yes. Got it. I was confused.
Yeah.
Sir, the
Yeah.
sigma field is for continuous also, right?
Yeah.
So it will have incountably many
Yeah.
elements.
Yes. Uncountably infinite, uncountable number of uncountable subsets.
Okay.
Okay. Power sets are only so sigma fields. Just check this, because I know that sigma fields are defined for continuous sets, but I don't know whether power sets are defined for continuous sets or not.
No, no,
Just
power
check.
sets is for discrete only.
Okay. For sets, and for a discrete set, the power sigma field reduces to a power set. So so a sigma field B for a sample space omega having events E, or actually, before I define these properties, so the events we mathematically define an event as an element of the sigma field so note this E is a subset of omega. E can be a subset of omega, but E is definitely an element of B. And mathematic and in probability theory, at least, or what we'll be discussing, the subsets of B have no significance. So do not confuse the elements of B and the subsets of B. Fine. So
Yes, sir.
yeah, the property. So now the sigma field B defined over sample space omega and constituted of the elements E or events E has I should write E bracket में this within brackets it should be E is a subset of has the following properties. It has the following properties. 1. Omega is an element of B. If E is an element of B, then E complement is also an element of B. So Rahul, the property that you were talking about. This is it, right?
Yes, sir. Yes, sir.
Yeah. 3. If EI for I equal to 1 to n are elements of B, then union of is also an element of B. Fine. These are the properties of a sigma field. So now define the probability measure. So measure theory, you have done analysis, right?
Yes, sir.
Yeah, so were measures introduced? Measures integration? No, integration you would know.
Yeah, integration was, but
No,
measure integration.
integration means that you would know integration where you split the x-axis so you can get the area under the curve, right?
Conditional integrations.
No, 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 no. So there are two forms of integrals. So one is the the integration that you would be doing right now is y dx or f of x dx means that you split the x-axis into small deltas and approximate those y's, and then so f x delta fx times delta x summed over all delta x is the integral, right?
Yes,
That's
sir.
the
Yes.
definition of integration that you are using. I cannot remember the proper name for that thing. So just a second, let me Google it.
So are you speaking about CDF or because
No,
it
no,
looks
no,
like
no, no,
CDF?
no. Don't jump. Don't jump.
Okay.
Common rectangular, like making them small rectangles and
Yeah.
adding.
So
That.
there's a word for that.
Is it a Levick measure?
No, Lebesgue integral is the other one. Lebesgue integral is something that you haven't done.
Have done in minors.
You have done, okay, you have done Lebesgue integral in minor. Yeah, the Riemann integral. The other one is the Riemann integral.
Yeah.
Yeah, so you are familiar with the Riemann integral. I couldn't remember the word Riemann. Yeah. So I couldn't. Yes. So the Riemann integral. So you have done the Riemann integral, but Lebesgue integration we'll touch upon in the course on digital communications. So I hope I get to teach you digital communications as well next semester. So there we'll talk about measures and Lebesgue integration. Till then we can skip. So yeah, we now define the probability measure. Your book calls it P, but for convenience and because P is used for many other things as well, I use the word PR on B as a set function assigning would I remove these brackets? Yeah, I put these brackets. Non-negative values to all events E in B. So that the following conditions are satisfied, and so I write this as PR actually is a mapping. Actually, yeah, this is a closed set because 0 and 1 are. So this PR is a mapping from 0 to 1 such that for all B this probability of the empty set equal to 0, and if EI intersection EJ equal to the empty set for all IJ I not equal to J, then a cleaner way of writing this would be limit n tends to infinity that contains all n probability I equal to 1 to n EI summation I equal to 1 to n probability EI. This beast. The triad based on these, oh sorry, triad omega B is called the probability space. Fine. This triad is called the probability space. I believe that this is enough abstract mathematics for one day.
Yeah.
Yes, sir.
Yeah. So this is enough abstract mathematics for one day. So let us stop here and continue tomorrow. I'll stop recording.
Sir,